All right, welcome back. Let's get started. So today's lecture, we're going to talk about a slightly different topic than the sort of hardcore formal verification we've been looking at so far in this class. And in particular, we're going to look at this sort of area of work called static analysis. And in some way, you can think of static analysis being the sort of lightweight cousin of the full-scale formal verification we've been looking at in lectures. The cool thing about static analysis is it's very widely used. So almost all serious development uses some kind of static analysis tool to catch bugs at some point in the development process. And moreover, it's a pretty active area of work. So you'll see lots of new static analysis tools and ideas being developed. This is sort of where we are in this lecture. We're reading these two papers that you hopefully took a look at, which are basically case studies of what it takes to apply various static analysis techniques to serious software development processes. And these case studies are from Google and Facebook, as you've seen. And they're actually surprisingly nice complement to each other in terms of the papers. So the papers actually cite one another effectively, and we can talk about how these two approaches compare and what's going on there. But to get started, I wanted to get you guys to discuss this question that we assigned about the reading, which is to say, what are these specs? What are these tools checking in the software? And why is it sort of falling short of the full formal verification that we've been focusing on in this class, and actually what makes it scale as opposed to some of the heavier weight approaches that we've been looking at. So does that make sense as a breakout task? Any questions before we jump in? All right, so let me assign here everyone to some breakout room, and we can get going. 1 second. All right, so I'll assign you guys and see you in 10 minutes or so. All right, I think we got everyone back now. So, what do you guys think? So, what's the deal with the specs in these static analysis systems? Are there specs that they're checking for? Anyone want to jump in, or I'll pick on some names?
Well, it seems like, they do have specs, but it's kind of a lot more like focused on certain properties of code rather than modeling the entire program. So like some examples they had were like type checking or, checking, are there any unused variables? So it seemed like the people who are writing the tools to do this static analysis had to know what kind of patterns to look for that could be bugs. And that was what the tools actually checked for in the end.
Yeah, so that's a good point, actually. Like, I think a big story here, or we can try to set up various tensions and see what the differences are. So one thing you really mentioned is sort of partial specs. They don't capture the whole notion of what it means for Facebook to be correct or Google is correct. It's like far off from what they're doing, but they're really looking at very sort of partial aspects of the code, something like this, versus the kind of full notion of what it means for a system to be correct that we've been looking at. So certainly this tension quite a bit. So they're not really looking for full correctness, as you mentioned. And the other thing I think you hit on is this sort of getting the developer involved. It's kind of interesting, right? In the Amazon or CompSearch style, the developer is intricately involved in writing a spec, but somehow here, the expectation to some extent is that the day-to-day developer writing the code isn't really involved in writing a spec, but the tool developer nonetheless really sort of works closely with these guys writing code to figure out what are the sort of things to check for. So some kind of co-design going on, the spec or this property versus sort of write full spec from the get-go. Yeah. Any other sort of aspects you guys picked up on from these papers or comments? I'll pick on, hey, Kevin, what is your take on the specs here?
I don't know. I feel like it's very heuristical, and so I don't know. And then there's like no like full like when you get something that it's not like guaranteed to be like, oh, this is going to be a problem. It's a lot of like false positives and also like false negatives as well.
Yeah, so one way to think of, I think what you're getting at is that indeed, like they don't really have specs to the extent that violating the spec means that your thing is really bad. They're really going for some kind of, heuristics or maybe some kind of, universal properties that you would expect every piece of code to have versus, app specific specifications. So their kind of specs are, I don't know, for lack of a better word, kind of like motherhood and apple pie. No one can argue that, yeah, that probably seems like a good idea, but, details matter, and maybe this is not the right heuristic or the right universal sort of notion for every piece of code out there. So you see, indeed, a lot of discussion ends up talking about false positives, and with a spec of the kind we saw in Amazon or CompSearch, this wouldn't be an argument. Either the spec's wrong or the code's wrong. There's no other third option. Like, if something is wrong, then you got to really fix this. Whereas here, it's really much more of a suggestion, if you will.
I think another way to think about this, like if you go to these papers, they talk about the goal. There's not really a spec as much as there is a goal of helping developers. And insofar as these tools are useful to people, they are doing a good job. And kind of as an intermediate heuristic, we have this idea that, okay, like race conditions are bad because like for various reasons, they make developers' lives harder.
Yeah, that's a good point. Like they don't have a goal of proving correctness, or they do have a goal of making software better, but only in as much as their tools help developers get there, not that they want to circumvent the developers or force the developers to do something that they don't appreciate or don't want to do.
In fact, I think it's the other way around. They put a heavy emphasis on not having false positives because the developer, if there's very many false positives, the developers assume that the tool is crying wolf, and then they either bitch loudly or they stop paying attention.
Yeah, so certainly the Google paper makes a huge deal about false positives, and we'll get to that. And actually, it's kind of a nice, almost contrast to it. The Facebook paper actually almost brags, like, look, we have this analysis, it's 50% false positives, but it's so great, the developers still love it. But it's more of an example, like, you still want to care about false positive, and they're just saying, well, this is sort of as high of a false positive rate as they're able to go to.
How do they, I can't remember what they say about how they deal with that, since they keep running the analysis over and over again.
So they do quite a bit of incremental analysis. So I think part of the reason why I think Facebook does a lot of their analysis on the review side is so that they can report diffs in the reports as opposed to full reports. So they talk about this whole hashing of a report. So there's a hash signature of what the bug is based on some fuzzy hash of the code, locations, line numbers, all this stuff. And if the fingerprint hash of the report is the same, they don't report it again. So there's something a little bit funny going on behind the scenes there, I think.
Well, maybe the main thing that's going on there is they have to have some way to deal with that 50% false positive rate.
Perhaps, yeah. So there's maybe that, maybe something going on there, yeah. So another interesting thing I thought, I was trying to think of this paper from the first principles of external actions, but actually the kinds of specs these guys worry about are very different. So these guys are very much about internal stuff going on in the program versus the kind of external behavior that we were thinking as a spec being in previous lectures. So in that regard, their specs are really not so much the behavior externally of the system, but really much more of some kind of an invariant that an application should follow. And these are sort of, moreover, these are not app specific. They're really sort of universal invariants that every application should follow. You shouldn't dereference a null pointer. You shouldn't send untrusted user input to a web browser in the Facebook case, etc. So their specs are much more low-level invariants on internal actions of a system as opposed to sort of visible external behavior. Make sense? Any other thoughts on sort of what's going on with these specs? What actually makes it fly? Why are they able to pull this off? Whereas CompSearch and Amazon seem almost like outliers. Well, wow, they were able to do that super impressive thing. So I think one other thing going on in their specs or sort of checks is really a huge degree of locality. So their specs are really invariants or checks you would make over fairly local bits of code and local bits of execution versus sort of whole execution behavior specs that we've been talking about so far. So with their checks, the reason it works out well is they're mostly relatively small scale properties that you can examine a small chunk of code and understand, oh, there's a problem here, or there's a likely problem here versus there's a likely not this problem here. So the whole notion of locality, I think, shows up in many ways throughout these papers that you see and makes us fly. And one thing I think some of you guys hinted at as well is this whole focus on practicality versus completeness. So what I mean by this completeness is that instead of sitting down first and saying, well, here's the thing we want to check and we'll just get there and then go and figure out how to make it happen, they really co-designed this very much with practicality in mind. So if something seems difficult to check for in this local internal invariant style, then they might say, well, you know, that's too bad. This is just not a thing we're going to check for. And it's much more of an opportunistic thing. Things that work out well, they keep. Something doesn't work out well, yeah, not the end of the world. So there's not this top-down insistence on any particular set of checks or rules or specs. So any questions about this list or sort of discussion about what are these guys checking for? Any other interesting things you guys ran into in your breakouts? All right, so we can talk about various sort of takes on these case studies. You know, these are sort of very large systems being described here, and there's not a whole lot of super technical detail being given. So this is inevitably going to be, you know, looking at various angles of this to the extent the paper describes them. So jump in with questions, whatever seems interesting to you guys, we can talk about and try to dig into that. But one dimension by which I was thinking we could try to do this is by looking at this case study that Google presented. So in the Google paper, they had this case study of the find bugs system. So this was an academic research prototype that was developed to find bugs in Java code. And the authors of the system, I think, actually went to Google. I'm not sure about the exact details, but they spent serious effort trying to get Google to use this find bug system to find bugs and fix them and ideally improve the quality of their software. And they described basically, well, from the paper's perspective, 3 failed attempts, 3 ways they tried and failed to get find bugs to really improve the quality of software. And it's kind of interesting to, you know, I'm going to talk about this from the perspective of the Google study, but actually Facebook echoes quite a number of these issues as well. And we can talk about the things that they show up in common and the things that differ. So the first thing that the Google guys reported doing with this find bug system was they set up this dashboard. So the way this worked, as far as I can understand, is that periodically, like every night, they would run find bugs on the entire source code or all the Java source code that was in scope for this tool at Google, and they'd produce a nice web page, and the developer could go there for every file. They could find what are the warnings, what are the issues found by this tool. And the paper basically says the developers ignored this thing. So what went wrong? Why didn't this work out so well for them? Any thoughts from having seen both papers?
I think the culture of like, oh, or like the idea of context switching is like when you do check for bugs and then like you have the report a day later, like developers are just lazy and they don't actually want to fix it.
Yes, I think there's a lot of common themes that we see show up here. So the Facebook paper is actually pretty great at these pithy sort of formulations of what's going on. So I think this context switch overhead is a serious issue for many of these tools. So if you put up a dashboard and the developer, they wrote this code at some point for sure, but might have been last year. They don't really care about this code. They've moved on to something else. So they're not as excited for you to tell them, well, you really should have done this nicer thing instead, or maybe there's a bug there. And especially with the fact that these reports are not really issues that your customer is having. These are sort of tool reports, and the tool says, well, maybe there was a bug here, who knows, maybe it actually matters. So I think there's a lot going on here with this context switch cost. And the interesting thing is actually the Facebook paper reports very similar numbers. So they basically say they also deployed a dashboard-like thing initially, and they basically quote the 0% fix rate. They have slightly different terminology, but the result is the same. They put up a dashboard, no one really cared. And it seems like this was certainly a common theme across the two papers. One sort of interesting, surprising detail, like sort of went the other way, which is that actually Facebook made this work eventually. So Facebook actually talks about this master list or master bug list that they produce periodically. And the way they made it work is that this master bug list is actually owned by the security sort of engineering team. And those guys actually care about the master bug list, partly because they worked, so the security engineering team worked closely with the analysis group to produce a master bug list that they think is valuable for them. It really helps them find security issues. So this team looks at this list and uses it to find likely bugs they should go after, and then they go jump in and try to figure out what to do with this bug once they've spotted it. Make sense? All right, so that was certainly one interesting sort of failure mode of dashboards, in the sense that sort of, I think this context switch overhead you brought up from the Facebook paper is a good way of thinking about it. The other thing that the Google guys reported doing with this Find Bugs project was that they would actually like file bug reports. And I think intention was that instead of having the dashboard be a place where the developers have to be excited to go there and find bugs in their code, which sort of worked out for Facebook eventually in this sort of security engineering team, they would actually go to the dashboard. But the Find Bugs people thought, okay, well, let's file bug reports. Then at least this will be, we're telling the developers, hey, there is a problem there, you should go fix it. And again, it seems like the response from the developers was that these bugs are sort of not worth fixing. Partly, I guess, because they're thinking, well, maybe they're not real bugs, or maybe these are bugs that don't show up in practice, or not the highest priority issue. It's not like developers are sitting there twiddling their thumbs thinking, well, what should I do today? Probably they all have their own projects going on. So these bugs really have to stack up there somewhere with respect to the other things they worry about doing. So this was a problem for them. And actually, sort of Facebook also reports a similar issue. So they also tried in some iteration of their tool this approach of filing bug reports or assigning these issues to developers. And here, sort of, I think the quote from the paper was this near silence. So indeed, developers don't seem to get excited about these mechanically filed bug reports from the analysis tools. So the other thing going on here, I think that the Facebook paper really brings out, that the Google paper I think doesn't articulate quite as well, is the question of who should fix it. So both with the dashboard issue and the bug report filing, it's not clear that the person that sees the dashboard or that gets assigned this bug report is necessarily the person that cares about this code strongly. Or maybe they used to care about this code, but they moved on. So there's not as big of a sort of connection to the right engineer at the right moment for these filed bug reports. Make sense? Thoughts or questions about this? So one other thing I wanted to mention.
Nikolai,
yeah,
I just went and read there's a Google published a report on this fix-it. There's a cited paper for the fix-it itself. So like they have an experience report about using find bugs. And they reported, they have something very interesting, which they say that the static analysis didn't really find any bugs that executed in production. It generally found bugs in unused code or in pads that never triggered. And they report this, they chalk this up to the success of their production monitoring, actually. So basically, like, people deployed bugs and then they were found and fixed.
Yeah, so that's a good point, right? Like, so just to sort of, maybe set the context here on the side, right? Like, how do people really deal with the bugs? And it's not like these static analysis tools come out of the blue and say, "Hi guys, we've discovered bugs. You gotta fix them." Like, everyone's known about bugs. They've been trying to find and fix real issues from the get-go. And there's a lot of stuff going on, right? So as we've talked about, there's testing, and there's, of course, unit testing that developers write for small pieces of code. Then there's sort of larger scale, maybe integration testing. There's probably monitoring of systems as they execute. Closely related are sort of, runtime checks. Maybe you can think of them as being in the monitoring category, but you have a piece of software and it's running, either running some synthetic workload like a test workload or in production, and maybe you augment the code with some checks so you can check if something bad is going on. And there's lots of tools here that maybe find race conditions or overflows, and we'll look at some of these tools later in the class, but that's a pretty rich area for how to deal with bugs. And then the static analysis comes along and says, well, we'll try to find bugs as well, but they've come later. And the big strength of static analysis is that you don't have to actually get an execution to go down a particular path. So all these things that I've mentioned here, like testing or runtime checks, they're all situations where you got a system, you got to really get it to execute the code in question and make sure that it actually triggers a bug if you want to find the bug. But then static analysis, like the cool thing, the reason why you might want to care about this is really this for all executions, or maybe you can think of it as for all inputs. Lets you potentially check what might go wrong, even if you never construct a concrete execution that went there ahead a priori. And I think basically what Tej is hinting at is that in some cases, maybe extensive testing and extensive runtime monitoring actually solve this problem. So for situations that you actually encounter at runtime, maybe a lot of these tools will get you there. And sort of maybe the counterpoint to that, so I think from Google's perspective, that's probably true. They have a very extensive test suites, and from Google's perspective, a lot of their code is running on servers that they carefully monitor, and they can understand what workloads are happening, what bugs are being hit. The Facebook paper has some interesting, actually, examples of why they really believe static analysis is in a unique position to help them. And I think one thing going on is security, because for security, it's often not as good of a plan to rely on runtime checking to detect what kinds of attacks have happened before, and those are the attacks that will keep happening. So there's some value in security to discover new executions that the attacker hasn't figured out yet, but they might. And if you figure it out first, you can fix it. And if you don't figure it out first, the attacker can do some serious damage. So there's some argument why for security, the static analysis is really a valuable tool, more so than traditional approaches up here. Another sort of thing that's cool that's going on for static analysis, of the Facebook paper makes a case, is really on mobile devices. Because at least the Facebook paper argues that on server workloads, like what Google predominantly has, they have extensive insight into how the code runs, what kinds of bugs are hit. Whereas on mobile devices, they might not have as good of an understanding, might be expensive in terms of battery life, to instrument that code, to monitor it, to upload reports that might be private user data. So they think that mobile devices are maybe another context where static analysis has a bit of an edge in terms of being able to find issues that you wouldn't have perhaps thought to find otherwise or thought to check a particular execution path.
There's something weird about this whole discussion, though, because the classic static analysis is type checking, right? And the standard mantra for type checking is it finds the bug earlier.
Absolutely, yeah. So I think, right.
So never mind that testing might have found it. It's easier if the compiler finds it. So it must make a very big difference whether you deploy the check before or after you have deployed the code.
Indeed. So I think, yeah.
I think that's an equally important point in both of these papers, right? I think they both talk about like which bugs should you actually use static analysis for, and also that it makes the effort smaller, right? Because you find the bugs close to when they can be fixed.
Yeah,
so in the case of these runtime checks,
here on the right side on like one particular aspect of what kinds of bugs. But yeah, I think Butler is absolutely right. That static analysis has this other huge benefit that if you do it right and get timely reports, then maybe you can get the issue fixed quicker. You don't even have to write an extensive runtime checker for it.
Well, you might want to do that too, but
yeah,
but it seems as though it's going to be much cheaper to fix the bug if the compiler can point it out.
Perhaps, yeah. Yeah, so it might be that maybe what Tej was originally saying is that part of the story for why find bugs didn't get anything too exciting found is maybe they were looking for low-hanging fruits of some sort that somehow already correlated with bugs that Google was already finding on a large, fairly well-established code base. And it might be that the results would have been different if they tried to apply it at development time for new code, as opposed to retrospectively looking at a large code base that already has been battle tested and trying to find new bugs in there.
Yeah, so the conclusion of that paper was that there are all ongoing efforts to integrate find bugs into the code review tool and into the IDE.
Yeah.
Although I thought the other thing that the Google paper said was that it was the thing that worked really well was to have the checks integrated into the compiler.
Yes, I think another big thing going on is sort of, shorter feedback loop. And I think it sort of a little bit ties in from Facebook's perspective as an answer to the question of who should fix it. Because if you have a short feedback loop, then it's pretty clear the guy that just touched the code should fix it and maybe cares more and sort of fixes also this context switch problem as well, as opposed to these long time analyses like what find bugs was originally doing. That was a tough sell to context switch someone and to get them to care.
So it seems like the naive way of summing all this up was type checking works really well. And if you're going to do other stuff, you should make it as similar to type checking as possible.
Yes, I think both papers agree on that. I think they see many desirable properties in type checking, like it's compile time, very few false positives, and the false positives that show up are probably worth fixing anyway.
But I would say one difference is that type checking is all or nothing, right? It's actually a blocker. And so that prevents you from deploying analyses that do not have 100% confidence.
Well, the Google guys actually say something about that too. They say that they had this, what I thought they said was a fairly successful project in which they had a team that would try to discover bad things, fix them in all the deployed code, and then deploy it as a compiler error, not warning.
Yes, yes.
Yeah, and they mentioned that in some cases they actually even have this as a merge blocker. If you flag any warnings from the analyzer, no matter if you think they're stupid, you should fix them. And then maybe if there's too many stupid things, then we'll pop up a level and remove this tool altogether. But as long as things are going well, they enforce this very strict discipline.
I guess the one thing I'd add to your statement, Butler, is that these papers are both advocating, I think, for a spectrum of checks, ranging from compiler must fix errors all the way up to diff time suggestions. They're kind of recommending don't do anything beyond that. Like, don't go through your old code.
Yeah. All right, so coming back to this list, one thing I wanted to mention in this file bug reports category, sort of basically didn't really work out for Google and Facebook for the most part, except for this one situation again at Facebook, which is sort of an interesting counterpoint, which is, they have some example where security engineers actually file bugs. So Facebook, if you remember in this paper, they have this funnel diagram of where the bug reports go. And one of the phases in the middle is that, well, maybe it's not the developer that just merged the code, but a security engineer periodically reviews all the warnings from the analysis tool and decides if any of these new warnings are worth turning into bug reports. And I think there's quite a bit of weight added by the security engineer, as well as an explanation of why someone should care about this bug. And those bugs really get much more attention when they're filed as reports, as opposed to these sort of naive things that find bugs did initially by filing just analysis output as a bug report.
This reminds me of a story that I heard from Bill McKeeman at Digital many years ago. He did the first effort to stress test compilers by generating all kinds of strange but syntactically correct inputs, feeding them to the compiler and seeing which ones caused the compiler to crash. And for a while, this worked extremely well. But after a while, the DEC compiler team told him to go away because they said, you're finding too many bugs. And most of the bugs that you're filing are not things that the customer is ever going to run into. If you nest parentheses 54 levels deep in an expression, maybe our compiler will crash. But no piece of customer code is ever going to actually do that.
Indeed. So I think this resonates with the comment also that Tej made about Google's code base much later, of course, now, that, yeah, there's lots of bugs to be found in cases that are in code that's not exercised or that's dead code or that doesn't matter in the actual deployment. And I think this is a serious struggle for Google, especially from the tools they're developing to make sure their bugs are judged to be worthwhile. All right, so going down this list of sort of find bugs, the last thing they tried was sort of code review integration. And this seems like a reasonable story. So when you submit some changes to be integrated into Google's code base, find bugs would run and report the issues. And here, it's kind of a weird story. As far as I can tell, the Google and Facebook papers basically both say this is actually, a good plan, except that the find bugs guys somehow had some problems here. So the Google paper reports that, as far as I can tell, for find bugs in particular, they somehow allow too much customization by developers. So developers were able to write specialized analyses for their own pieces of source code. And because these analyses didn't line up between projects, you got confusing warnings or it wasn't clear what to expect. So something along these lines went wrong for them. But it's not clear exactly, well, I don't really understand why this failed for them, because in the end, both papers actually say, oh, this is actually a good idea. You should do code review time integration of these analysis tools. I guess going down this list almost of when to report the bug, you can sort of see this gradient of reporting sooner or faster to when the code was just written. And the thing that the find bugs guys don't actually report, but the Google and Facebook papers, of course, do talk about, is compile time. And Butler and Tej have also brought this up. And for Google, I think for both papers, you can see compile time is the holy grail. As Butler points out, type checking is sort of what you want every analysis to look like. You just run your code and it sort of mechanically checks right when you wrote the code on your machine. But sort of the way the papers, I think, present this compile time option is almost a little bit two different flavors. So in Google, they basically think, well, every analysis really should flow down and hit the compile time phase eventually. So they almost think, well, let's start out by doing, review time analysis, and then eventually we'll get that down to compile time, if possible. I think for good reasons. In the Facebook case, I think what's going on is that the particular analyses that the paper really spends a lot of time talking about are, I think, kind of too slow and too costly to perform on the developer's machine. They really require more time. They sort of cite numbers like 15 minutes or so. So this is just, I think, at their scale, not quite feasible to run locally, and also requires some state to figure out what changed between the previous code run and the new code run. And I think Facebook probably would be happy if this was a compile time option just for them. It seems like they're aiming for too big of a thing to be fit in a compiler locally. Does this make sense? So this sort of way of looking at this set of issues. Comments, questions? I guess as I said at the beginning, it's not like there's, I think, any clear answers here in these papers. It's mostly discussing this case study, so feel free to jump in again. So one common theme that I think really resonated, that I think came up in our discussion so far, is really this, the goal being, solve a problem for the developer or the engineer. And Tej brought this up early on, right? These guys are not aiming to verify against the spec. They really want this to be a sort of a tool on the way towards helping developers really fix their issues. And there's, I think, many things that go into it. One is, of course, oops, what happened? Maybe my tool went away. Restore the file. All right, how about that? Crash recovery. All right, so I guess where we were is, I was gonna say, so solving the problem for the engineer, I think has to be at the right time. Well, that's a side effect of this crash. I got a new color, that's all right. So has to solve the problem at the right time, has to actually be sort of the, the right, insight that maybe the engineer didn't have or didn't catch. Shouldn't be just boilerplate stuff that the engineer already knows. And probably has to be also, the right developer or engineer that looks at this report and appreciates this from the tool. That seems to be a common problem or common theme that these guys hit on, is that you really got to integrate this into what the developer cares about. Questions? Comments? All right, so that's one sort of facet we can look at. Let's try to sort of talk about this maybe from a little bit of a different angle. So again, in the Google paper is good for these almost checklists that they sort of articulate for how to build such tools. So the Google paper describes almost, I think, these pitfalls and how to avoid them. Well, that was a buggy piece of code. Let's restore this file again. So there's probably some bugs that Google sort of ran into in deploying this, and how to avoid them. Seems like a good question to look at. And we can sort of look at the big thing they say, I think, is really this integration with the developer workflow. So they hit upon this many times, and this actually resonates with what the Facebook paper talks about, is that you really have to insert yourself in the right place. And I guess, as we talked about, ideally compile time, or maybe if not compile time, then at least review time. And maybe file bugs. That seems maybe possible, but worse than review time. And then sort of the worst of all outcomes is really you do batch analysis. So this is the sort of the dashboard view that Find Bugs initially tried. And one interesting thing is how Google and Facebook approach this batch analysis almost differently. So Google really thinks of, or the paper really presents this as, well, the batch analysis is the thing that the tool developer runs. And it's actually incumbent on the tool developer. They must look at this batch analysis output, fix all those bugs before they can enable this tool to be run at review time. So for Google, their sort of view is, you take the batch analysis and you fix all the bugs first, and then you sort of move up the stack. So as you get more confidence in your tool, you should really push this tool closer and closer, partly because maybe it's faster, and partly maybe you can enforce it stricter because you have higher confidence that these bugs are real or worth fixing, and so on. Facebook, I think also, it's not like they would disagree, but they have this interesting view of that, well, there's actually a valuable way of running the batch analysis, which is turn the batch analysis into bug reports. So I think there are certain workflows around security in particular in the Google paper, in the Facebook paper, where they think it's really valuable to do these batch analysis and file bugs from them instead, perhaps because they don't really see this as being viable to move it up the stack for cost or false positive reasons, etc. Make sense? Any questions about that? All right. So another thing that the Google paper mentions in terms of things to avoid is really this notion that you have to have actionable warnings or reports. So it must be clear what the user should really be doing with this analysis outcome. So some of these things sound like good statements, but not super clear what they mean. I think for actionable warnings, the thing I think they mean is that you don't really want to have reports that relate to legacy code that the developer didn't change. So if you have a false positive, or maybe not even a false positive, just a report for a piece of code that's been there for years, and some developer comes around and changes the code nearby, and now the review system says, oh, well, here's a warning, you got to fix this. It's maybe not actionable in the sense that this paper talks about, because this is just a sort of an annoyance to the developer. They don't know what the heck this other piece of code is doing that triggered the warning. They're just editing some code nearby. So that might be one thing that they mean by actionable warnings. Another sort of result of this is sort of this arrow up that I tried to draw over here, is that I think the Google paper really articulates, you got to fix the bugs or sort of warnings before deploying a tool. So here you really see this sort of centralized repository coming into play. So for systems like for sort of development environments like Google and Facebook, they really have a single repo that's got all the code. And this makes it possible for the tool developers to precisely understand what the actual software developers are facing, what code they're writing, what bugs they're fixing, what needs to be fixed in order to deploy a tool, what would the report rate look like if we were to enable this tool. So it's much closer integration, in contrast with something maybe a more of an open source approach where you have lots of developers, some tool developers writing a tool, but they have no idea. They can't even look at the code that their users are going to use the tool on. And they have to release a tool, and then the users come around and say, well, I got a weird code base. Your tool reports all kinds of errors on it. What the heck? So this is an experience that I think the Google and Facebook teams are able to avoid, because they can sort of prepare the tool or prepare the code base before flipping the switch and moving it up some analysis tool to this review time mode. All right, yeah, comments?
I have a cute story related to this. That so I interned at Google, and I noticed that there's some of the code uses this pattern of basically saying assert false when there was already a macro for just fail outright. And so I was like, okay, this seems bad. We should fix this. You should just always use assert fail. You should always use fail and not assert false. And so I looked up the large scale review process, and I started the process. But then they came back and told me there are only 100 uses of this in the entire Google code base. This is not a large scale change. We will not fix this.
Huh, interesting. So yeah, that's a I guess, yeah, there's all kinds of like maybe one.
But it's right. One reason why I want to point this out is that it's pretty cool. Like they're actually able to assess that this is a small enough change that it's not worth creating all of this fuss.
Yeah, so there's
Indeed,
I think there's like some serious things that are enabled by this, by having access to the code. From the open source world, I think the closest analogy is the Linux source tree for the Linux kernel. And there's a lot of software in the Linux source repository that could probably live elsewhere, like device drivers or special file system implementations. But there's a lot of benefit to having all the software in one place, and anytime someone makes a change, they can find all the users and collect them all. And I think this allows the Linux kernel to evolve much faster without rigid interfaces, which is sort of both good and bad. If you have a driver that's outside of the Linux kernel source tree, there's much less of a rigid interface to the kernel that you can rely on, in contrast to something like Microsoft's Windows, which has extremely backwards compatible interfaces because not all software lives together. For Linux, it seems a little bit closer to this Google world that you described, and you can just assess, well, this is a reasonable change to make, you can do it quickly, this will break something, this will not break something. Yeah. That's kind of an interesting other universe to live in, very much quite different from classical, tool development, where you give a tool to someone, they'll use it. So another point that Google makes is really about user trust, and you sort of see this show up as well in the Facebook paper. They really, I guess in the Google case, the focus is really on avoiding false positives. And avoiding false positives, interestingly enough, Google sort of almost definitionally equates a false positives to action. So this actionable warnings above basically means it's almost the definition of a false positive. If a developer goes through and does something, that's good. Doesn't matter what the underlying truth was. Was there an issue? Was there not an issue? It doesn't matter. If the tool causes action, that's good. And Facebook has a little bit of a different story that they pitch in the paper, even though, I should say, like one thing going on in the papers, I think they're focusing on particular takes on the static analysis work being done at these companies, but I'm sure there's much more overlap than what the papers hint at. So one impression you might walk away from is that, well, Facebook really goes for these deeper properties that require interprocedural analysis and taint tracking, and Google does sort of lint checking and type analysis and so on used variables. But I imagine the sort of story is much more broad and heavily overlapping. So Facebook, there's like one paragraph in the Facebook paper where they say, actually, we also deploy a bunch of linters and all this other stuff too that basically Google is doing. And I think Google also has these maybe more narrowly focused teams that do more in-depth analysis, closer to what the Facebook paper is talking about. So it's not so much that they differ, but the papers at least differ. And in the Facebook paper, the way I think they aim at user trust is maybe less so in sort of definitionally saying action and avoiding false positives, but really, pick maybe teams that care about a particular problem or problem statements that are hard to solve otherwise, and really go help those specific teams and focus on their needs, as opposed to sort of a blanket, low false positive rate for everyone. And sort of related to that, I think is the Google paper says one of the pitfalls is you got to really make sure your the bugs you report are relevant and fixable. The fixability, I think, is closer maybe to this actionable warning business, but the bugs really have to be sort of things that will trigger at or matter at runtime, or maybe so easy to fix that you should just fix them anyway, even though they might not matter. So the sort of trade-off of bugs importance and how hard is it to go and fix it, I think is a big issue for both these systems, although you sort of see, I think, the paper is focusing on different angles again. I think on the Google case, they really focus on the fixability being low. So push it to compile time, really try to make it so easy for the developer to do the right thing and just avoid the warning. Whereas I think on the Facebook case, they push a little bit in the other direction of importance or relevance. They really go for problems that the developers really care about and think, well, that's worth the warning. And maybe it's a little bit more effort to fix, but the developers seem to be excited about that anyway. And the last sort of amusing point that the paper brings up, and important despite being amusing, is that your users really have to understand the warnings. And it doesn't matter basically if the tool is right. If the developer doesn't understand what the heck the tool says, they're not going to fix it. So the sort of cute example I think that they give from a particular system where you could do printf style, messages. So you can print, %s, print a string, print a number, print another string, and then you would say, X, Y, and Z, pass those to the arguments. Except that the system in which they were doing this checker it was a weird system. They basically didn't allow %d specifiers. Actually, the only thing they allowed is %s, according to the paper. So the tool would look at this and say, well, there's only 2 positional specifiers. There's only 2 %s's here, and you're passing 3 arguments. And their message said, well, you got to pass 2 arguments instead of 3. And basically, their experience was, from the analysis perspective, all the developers thought the tool was stupid. It's like, look, how stupid can you be? There's a %d right there. Why can't you count? And as soon as they changed the error message saying this printf function only accepts %s specifiers, then all the developers, the bulk of them, understood their reports much better and actually fixed these issues, as opposed to dismissing the bug as a false positive or some kind of a tool issue. So that was kind of an amusing anecdote in terms of the I think really developers really have to build quite a bit of trust, so this user trust. Like it's not maybe a stateless property once you have users that are engaged with the tool and appreciate how it works and understand when to trust it, when to not trust it. I think it might be that the warnings will get a slightly different reaction from developers. Make sense? Questions about this sort of pitfall view of the world that Google put forward? Comments? All right. So I think so far we've been looking at things that are pretty similar between the two systems. One big difference, though, is I think in terms of the focus or metrics that the two papers put forward for what makes for a good analysis tool. So the Google paper really pitches this thing they call the effective false positive rate. And for Google, this was just a completely holistic end-to-end measure of whether the tool is doing good stuff. So effective, EFP. That's the metric for them. And the sort of interesting thing that I was kind of amused by is that if the developer fixes some nuisance warning, then that's actually perfectly fine. So the developer sees a warning and thinks, well, it's not really a bug, but I'll fix it anyway. Then they basically say, well, it's not an effective false positive because the developer did something. A very action-oriented definition of what it means to have a good report. And at the same time, if you have some developer that got a warning but missed a real issue, well, it doesn't matter that it was a real issue. It's a false positive because the developer didn't do anything with that report. And the sort of amusing tidbit for me was that they really have like a flag button. If you have a not useful report, the developer can click this button in the code review tool and say, well, I don't really think that was useful for me as an analysis output. Doesn't matter if it was right or not. You can click that button, and the analysis team, I think, as far as the paper suggests, they will actually take out analyses from the system if the analysis generates too many reports that developers click not useful on. Very user-oriented, developer-oriented system in that sense. Another sort of interesting tidbit I saw from the paper was that there's almost like first lesson is there's always bugs. Whenever you look, you'll always find more bugs. And the whole paper, you can almost view it as an exercise in dealing with this endless stream of bugs. So what do? We got all these bugs coming in. We look for this, we find bugs, we look for this other thing, more bugs everywhere. How do we report these things to the user? And one, maybe not an entirely fair characterization, is that this leads to these kinds of, unobjectionable bugs, if you will. So the metric here really drives you to report bugs that developers will fix, and it doesn't really matter if how perhaps significant it was, at least from this metric. I'm sure I'm not entirely being fair to this Google paper, but sort of maybe a good way to see the contrast with what the Facebook guys are talking about. So the Facebook paper really makes a deal of missed bugs as their big metric. So they don't really cite false positive numbers nearly as much as the Google paper. They really talk about are there bugs that we shipped or that had happened in production that our tools didn't catch? And to them, that's sort of the mindset. They really want to avoid situations where they could have prevented an issue but didn't. So the paper even has this sort of statement of their, I don't know if it's a goal or not, but like, how could this be prevented in production? So if they see a bug that happened and caused some problem for them, they really argue the right question to ask is, how could we have caught it with some kind of an analysis tool? And slightly different focus, and I think also shows up in terms of the kinds of bugs that they go after. So instead of going for these, I'm like oversimplifying, the unobjectionable bugs from the Google paper, I think the Facebook paper really talks about focus areas. So particular problem domains where the developers really are asking for a tool or want some assistance to find bugs. So I think one thing they talk about sort of upfront is crashes. So if you reference a null pointer, that seems like a real issue. Security is one domain where they have a whole team that seems to be very happy with the analysis coming out of the results coming out of these analysis tools. They really use it effectively. They talk about sort of concurrency being one place where the paper actually had this interesting anecdote where the team that was developing some concurrent piece of code, basically multi-threading the Android app for Facebook, roughly speaking, or something like this, they really came to the analysis team and said, hey guys, we got this problem. We're creating concurrent software. We think there's going to be bugs. Help us find them. And they really, I was shocked how effective they seem to have claimed this approach works. So, if you look at the metrics they report in the paper, that's just shocking. Basically, they say, well, we looked at these concurrency bugs. They say, well, over the last year, we had 3 data races that were not caught, that were missed bugs. And those 3 data races, they say, well, it's actually because we have like a kind of an error in the analysis tool. And if we didn't have a bug in our analysis tool itself, we would have caught that data race. That's just shocking to me. Extremely effective for a fairly sophisticated kind of bug. It's like a data race. And admittedly, maybe it's in stylized code, but still, I think this is quite a bit of a difference from the focus that the Google paper puts on things, where the focus there is on false positives. And as a result, we actually have this surprising thing where the developers actually tolerate false positives quite a bit more that are higher up. So I think for this concurrency story, the developers for this concurrent rendering software in Java, I forget exactly, it's some kind of a mobile app that does rendering of nested UI elements. They actually say that they run this analysis tool, and actually 50% of the reports they get are actually false positives. And it's a little bit hard to say what the definition is, whether it's the effective definition that Google puts forward or something else, but it's kind of impressive that despite half of the reports being not acted on, I'm guessing, the developers think it's valuable, and the paper argues that developers like it because the developers appreciate this is an extremely hard problem to avoid race conditions in concurrent software, and the developers really sort of appreciate these reports, even though half the time it turns out not a serious issue, because presumably they're thinking, well, like the half the time it hits, man, that's not a bug I would have found myself. So
maybe Google people aren't writing concurrent software.
Somehow I doubt that. I think, okay, so one thing maybe that's going on is Google people aren't writing sort of as maybe complicate of a mobile app, although they're writing all of Android, so that can't really be any less complicated than the Facebook Android app itself. I think it's really just the focus of the papers. I think there's teams at Google that are probably doing serious analyses that along the lines of what Facebook talks about and vice versa. Facebook has probably a broad-based analysis and linting platform as well. So I sort of take this more as a difference in the paper angles as opposed to somehow the two engineering organizations have different cultures here. If anything, I would have guessed the other way around from some bias about Facebook versus Google, but I don't know if anyone has sort of insights as to what's going on, why, if there's sort of deeper analyses, examples of deeper analysis that there's papers about at Google. I don't know offhand of anything. Yeah. All right. So the only other sort of thing I wanted to add in this category is actually like in the security category, which also seems like a huge sort of pile of security issues that you could have, especially for all of Facebook written in PHP or this fancy version of PHP. Seems like it would have been riddled with security holes, but no. There's this like shocking statistic, like only 11 security bugs were missed by their tool. Now, there's like a lot of asterisks here, of course. These are only bugs in the categories that the tool looks for. So I'm sure there's security issues that Facebook could have that the tool isn't even checking for. But it's extremely impressive that even in the categories that they choose to focus on, they're able to get such low missed bug rate. That's a really cool outcome. Would not have guessed that would have flied. Any thoughts or comments on this sort of angle on the focus or the metrics that these two papers propose? At the end of the day, they're probably all unified by this thing that we talked about of helping developers. But I think they're almost helping developers in almost two different axes. Google is helping across development teams, like nibble on everything across every development group and make sure to fix something. Whereas Facebook seems a little bit more vertically oriented, pick a category and really go for that narrow category. Both seem important. All right. So last thing I wanted to maybe talk about is this sort of focus that Facebook has on these interprocedural analyses. So just to give you guys some flavor of what it is that the Facebook paper talks about. So interprocedural bugs are somewhat more tricky to catch or to sort of reason about than the localized reasoning. So early on, when we were talking about what are the specs these systems are looking at, we were talking about local bugs that can be caught by sort of a fairly myopic view of the code you're analyzing. It turns out not all bugs are like this. So there's like two bugs that the Facebook paper talks about. One is this null pointer dereference, where they look at the OpenSSL library, and there's some kind of a function x509 gm time adjust, and take some arguments. And what happens is that inside the function, there's a lot of function calls. It calls some function f, calls g, calls a lot of things, and eventually you get to a statement that says return null. And what happens is this null gets returned all the way up the stack to all these callers and ends up in this revtm variable. And then the code does something like I equals revtm length plus 1. And in C, what happens here is that this dereferences the revtm pointer. And if this could be null, that's a bad thing. Your piece of software is going to crash. This is the kind of bug that the Facebook team, the infer tool, was trying to catch. And as you can imagine, right, this kind of a bug is a little bit tricky to get to catch by looking at a small piece of code. Because if you just look at the function that contains these two lines and you don't look at all the other pieces of code that get called, you sort of abstract away this box, then in many situations, functions don't return null pointer. So it'll be crazy to flag every time you get a value from a function and dereference it. You'd get tons of false positives. But at the same time, sometimes it happens. So if you assume that it never returns a null pointer, well, now you've missed this bug. So a big deal for them is how to catch this. And the other naive thing is basically like expand out all the function calls is just impractical at the scale they're talking about, because they want to analyze millions and tens of millions of lines of code, and you can't expand out all the inline calls that your software makes. You will never finish, because you now have to, at every function is a million lines long. So there's something that has to happen here. Another example they give is actually this data flow analysis, where they have this function called render that is responsible for talking to a web browser, basically. So you get some web browser on the side from a user coming in. User makes a request to render some page, and render, gets some kind of an ID from getIDs, and this getIDs function internally, reads some input from the web browser. And then this render function passes this ID to another function like getForm, and this guy gets the ID argument, and eventually render you can think of as printing the out variable, and this printing goes back to the web browser. And the exact details are probably not going to be possible to explain in the remaining time here, but basically it turns out to be a security problem if you get some input from the user and you incorporate it in a web page without sanitizing it. So that's a kind of a bug they'd like to catch. And again, it's not clear if this is a bug or not if you look at the render function, because it might be fine. Maybe getForm does the right thing with ID, doesn't put it in a web page unsanitized. But then if you look at the innards of this getForm function itself, well, you're looking at this myopic view. You don't even know if getForm is producing a page that's going to get sent to a user or not. Or maybe ID is totally a trusted argument as opposed to having been just received from the user. So this analysis across functions is critical to finding some of these bugs that these guys are talking about. And this is what they mean by compositional analysis. So they really want to do analysis that that can catch these kinds of bugs, but without unfolding all the pieces of code with all their functions they're calling. And the core idea here is some kind of a procedure summary, which you can think of as basically some kind of an intermediate spec for every function. So in the example of this bug here with the null pointer, we'll need a spec for f, we'll need a spec for g, we'll need a spec for this guy. And same here, we'll need a spec for getID, for getForm, and for print. And having these intermediate specs, kind of like the Hoare logic specs you see in your lab assignments, is going to help us catch these issues without having to expand out our search space to the entire code base. And the really sort of hard problem is, who writes these intermediate specs? And the core contribution of Facebook's infer tool is indeed this inference. They actually deduce these specs through code analyses. So you look at the code of these functions, f and g, and they figure out what are the essential things to extract out from the code of that function into a inferred or deduced spec. Same for these functions like getIDs and getForm. The specs might be of the form that, well, getIDs can return an unsafe user input. getForm propagates whatever inputs it got here to the output. Print, the summary is it will return to the user. And these summaries can help you analyze code like this render function and convince yourself, well, there might be a bug here. And the hard problem here is not so much to make sure these specs are correct, because the analysis tool can probably check that these induced specs actually are matched to code in the function. The hard thing is figuring out what is a precise enough spec. Because if you got your spec correct but not useful, it might always flag everything as a false positive. A possible spec might be every function can return null. It's correct, but not super useful. The alternative, of course, is that you manually annotate things. So, for example, the Linux kernel actually has lots of annotations where the kernel developers think that some things are really important to get right, and they actually go through and annotate functions with arguments with things like what inputs can come from a user, what things can go out back to a user, etc. But this ends up being sort of the core of this compositional analysis problem, how to get precise enough intermediate specs for all the functions. And then once you have these intermediate specs, then you can actually get very nice properties because you can parallelize your analyses one function at a time. You can run them on one function instead of the whole code base, make it incremental, and generally sort of scale it to large systems. All right, so I think that's all the time we had. I'm happy to take questions, although since we're out of time, feel free to also disconnect and see you guys on Thursday then.